So what is holding all those little sugar molecules together into crystals and into clumps are intermolecular forces. It's forces between the individual molecules of sugar. So each little molecule of sugar, let's see, and we'll do just a 1, 2, 3, 4, 5, 6, a 6-chain sugar, and it's going to have some hydroxide groups and some hydrogens and who knows what else. Well, if we do glucose, I have no idea what the structure of glucose is. I'm making this up as I go. 1, 2, 3, 4, 5, 6. There. We'll say that's it. It's not. I know that. But if we imagine that that might be something like the structure of glucose. So within this molecule, it's held together by covalent bonds. Between this molecule and the next molecule just like it, there's got to be something else at work. We'll shrink these so we can make this happen. There has to be some kind of force that's, I just chopped half of it off, that's going to hold those two molecules together. And these are intermolecular forces. We can take a pretty good guess, we can estimate how strong those intermolecular forces are based on the boiling point of the liquid. So the stronger the forces holding two molecules of something together, the more energy it takes to break those and turn it into a vapor. So at the point when it's a vapor, we say that there are almost no forces acting between the molecules once something has been vaporized. So something that's got a very low boiling point, something that's a vapor at room temperature, for instance, would have very, very weak intermolecular forces. Something that's got an incredibly high boiling point would have very strong intermolecular forces. Can you vaporize sugar? Yes, you can. Yes, you can. Heat it up. And sugar's got, it's pretty easy to get sugar to boil. You can get it to melt, and with a candle flame in here, most of you got it to not only melt, but to start to bubble and boil and vaporize off. That's a relatively low boiling point. The intermolecular forces are weaker than the forces that are inside the molecule. So the forces that are holding the molecule together are much stronger than the forces that are holding two molecules together. Make sense? Okay. The forces between two molecules in any kind of molecular compound also are weaker than the forces between metal atoms. You know, which boils at a lower temperature, sugar or steel? Sugar. Yeah. Much weaker than the bonds that we see in a metal. And definitely weaker than the bonds between the ions and ionic compounds. If you remember comparing things like calcium chloride and sodium chloride to sugar and phenyl salicylate, those are molecular compounds, those boil more easily. We have dipole forces. So, do you remember polar covalent bonds? What's a polar covalent bond? Okay, it has a difference of electronegativity of between 0.3 and 1.7, that's true. But describe what it creates in terms of a molecule if we have a polar covalent bond. It creates a substance in which the electrons are not being shared evenly, right? Yeah. You're all like, I knew that. I thought you wanted something more technical. No, that's all I wanted. You know, it creates this substance where the electrons are not being shared evenly. The electron cloud is not being shared evenly. So, you know, in the case of our old friend Mickey here. Oops, I drew Mickey's oxygen a little too low. That's terrible. Still pretty bad, but okay. And of course, we know that from all of your construction, you've got a couple of unshared pairs here too. Oxygen is such an electron cloud hog. And let's see if I can do something that will represent the electron cloud. We'll make it yellow. No, that's too dense. So if water was not polar, it would vaporize much more rapidly. We wouldn't have liquid oceans on this planet. Lucky for us, huh? Okay. Now we have one other phenomena to talk about in terms of intermolecular forces, hydrogen bonding. So sometimes we have, and we're going to use Mickey again, our old friend water. So Mickey's got a couple other things going on here. So water's got oxygen as an electron hog. Oxygen is hogging up the electron cloud. But the other thing that's happening here is that you've got unshared pairs of electrons. Well, even if there were no hogging of the electrical cloud, hydrogen nuclei tend to be real attracted to unshared pairs of electrons. Hydrogen nuclei is just a proton, it's positive charge. And so anytime you've got hydrogen nuclei in the mix with a bunch of things that have unshared pairs, you're going to end up with those hydrogens lining up like 12-year-olds at I don't even know what kind of concert 12-year-olds would line up at these days. That's how out of the loop I am. What would it be? That's hydrogen bonding. That is different than dipole forces. Now, water happens to have both dipole forces and hydrogen bonding. And in the case of water, the hydrogen bonding is probably a little bit more important than the dipole forces, but they're both going on. They're both present. Again, hydrogen bonding. The boiling point in something that's got hydrogen bonding is higher than it would be otherwise. The other thing it does is it creates surface tension. So in a glass of water, where you have a surface, you know that you can float a piece of paper on that surface. You've all seen a piece of paper float on water. You've all seen little insects that have a very specialized niche who walk on water. Water striders, yeah. They're walking on the surface tension. They've got little discs on their feet. And they're light enough, they have low enough mass that they can actually rest on the water tension, because every little water molecule on that surface is so strongly attracted to every other one that until you get up to a little bit more mass, nothing even drops through. So those are, and there's one other kind of intermolecular force that we're going to talk about. This is the one that is sort of least relevant for us and least important. London dispersion forces. And these are just, there are some very weak intermolecular forces in things that are not polar. So things like rubbing alcohol. Rubbing alcohol is not polar, but there are still some forces in between it, or it would always be a gas. There have even been London dispersion forces. There are London dispersion forces between things like noble gases. And I know we think of noble gases as not interacting with anything in any way, but they do actually interact with themselves. And that's how you get a mass of argon or a mass of neon or helium. This is the textbook definition. Intermolecular attractions resulting from constant motion of electrons and creation of instantaneous dipoles. Basically what that means is, as the electrons are zipping around in their cloud, remember, the little chaos bunnies, they're all over the place, there will be moments where a bunch of electrons end up on one side of a molecule or on one end, that creates this brief flash of a dipole, and then it's attracted to something else near it. So these are like little forces that are sort of popping in and out all the time. So they're pretty weak because, you know, they're active, then they're gone. Then they're active, then they're gone. So they're not strong. They don't change melting points, boiling points. They don't do enough to create surface tension or anything. They're very weak. They're very brief, but they're there. So you should know that there are three big categories. These are the ones that I expect you to have the least familiarity with. Questions, comments, concerns? That's it, folks. That's chapter 6. So I'm going to give you the rest of the time today to finish up your lab stuff, study, work on things. Remember that molecular geometry lab is basically replacing a homework assignment for the latter part of the chapter. Labs are due tomorrow. Because that is replacing a homework assignment, here's what we're going to do. We will grade those labs in class like we would a homework assignment. And I'll be generous, we'll even do it in the second period that we're together. So if you've got things that you want to touch up or revisit with your partners, you can do that. And second half, we will grade those, go over them, answer any questions people have, and Friday's your chapter 6 test. So that's it.